I can't hear anything. Hello, sir, we can't hear anything.
You can't hear? Yeah, because I'm not talking. Good morning. You cannot hear anything because I wasn't talking before. I hope now that you can. Good morning. Welcome to our lecture. Can you hear something now?
Yeah.
Okay. Wonderful. I think, I don't know, when we last met, I believe we were talking about flip-flops. We were talking about the SR flip-flop. And if you we said that the SR flip-flop is based on the NOR gate, and it sets the flip-flop when S is 1, and it resets the flip-flop when S is 0. When R is 0. Okay, so it's actually here. And the 0, 0 input gives no change. And in fact, that also tells you that the S and R inputs are kept in the 0 state where they are inactive. And when you set 1 to a 1, or you put 1 as a 1, it will actually perform, it becomes its active state. And the 1 and 1 means that you're trying to set and reset at the same time. And that makes it ambiguous. So by ambiguous, it means you will not get reliable performance. Okay, thank you for that. I imagine you mean me. So we were talking about the SR flip-flop. We are going to continue today with a couple of other flip-flops, but I think what I really emphasized with the flip-flops is that these are synchronous devices, in the sense that they are actually they wait for the clock to happen before something happens at the flip-flop. So they are synchronized with the clock, so to speak. And the clock can be, so these flip-flops are actually edge triggered. By edge, I mean the transition from either, I just want, my pen is misbehaving. The transition, let me see, my pen is misbehaving. So the edge is transition. Basically, this is the edge. Okay, this is the edge. The clock could be transitioning from 0 to a 1 or a 1 to a 0. Okay, if it is transitioning from 0 to 1, and that is the edge that is decisive, we call this a positive going transition. If the edge that is decisive is when the clock transitions from a 1 to a 0, this kind of edge, we call this the negative going transition. And we said that once I have seen what has happened here, I know that the next, if this is NGT, if this is based on NGT, the next time something can happen is at the next NGT. I don't care what is happening in the middle here. I just look I look out for the NGT, 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 and whatever the state is at this NGT, it will remain or it will prevail until the next NGT, where it might stay or it might change. Okay. So let us look at the clocked JK flip-flop. This clocked JK flip-flop is essentially similar to the SR flip-flop. If you look at this truth table, the J is 0 and 0 causes no change. When J is 1 and K is a 0, you set the flip-flop. If J is a 0 and K is 1, you reset or you clear. So this is the clear state, and this is the set state. Now, the difference between the JK and SR flip-flop is in the 1-1. When J is 1 and K is 1, here we toggle. We do not, remember before, for the SR flip-flop, we said that this state is ambiguous because we are trying to set and reset at the same time. For the JK flip-flop, it is different. in the sense that the 1 and 1 states do not, a combination of 1 and 1 does not give you an ambiguous scenario. It actually toggles the flip-flop. By toggling, we mean that if Q was 1, it toggles to 0. If Q was currently 0, it will toggle to 1. So that's why here we have that we have Q naught inverse. So you take on the current. Q naught is really the current, or if you like, the previous state of the flip-flop. It just becomes the opposite at the 1-1 state. So let us look at this, and obviously the state of the flip-flop is the Q state. Okay, so the Q defines the state of the flip-flop, not the Q1, not the Q inverse. You need to remember that always, that the state of the flip-flop is actually the Q state. Now, let us look at this. We have the J. This is a timing diagram. We have J, we have K, we have our clock. And we see here that initially Q is a 1. So really what this means is that Q naught is a 1. Segawa, you're making noise for us, please. Okay, so Q naught is 1, which means that previously the Q naught, or the state of the flip-flop, was a 1. Now, we look for the clock. The next times, this 1 will prevail until the next time there is a positive glowing transition. You can see that this is actually a PGT. A PGT can be shown by this small pulse, which shows an arrow on the PGT, on the positive going transition. It can also be shown by that symbol, which does not have a bubble. And yeah, essentially. But usually also, when it is an NGT, we tend to say clock, okay, with a bar. So to give you that concept of a negative active state. Whereas here, you can see there is no bar, so usually that's okay. Now, here we notice that K is 1 and J is 0 here at this PGT, that is at A. Somebody is still making noise for us. Choncho. Please, when you come in, just mute yourselves. So because that is a 1 and that's a 0, we are going to clear. You can see that the state will go to 0, and that's a reset or a clear. Now, I don't care what is happening with my two inputs here. I just know that this 0 will remain until the next PGT. Okay, I look at this point at the PGT, I have a 1 and a 1. And in this symbol here, it would be with SR, it would be unambiguous, but now we know that it will toggle. By toggling, it means it changes state. And so if it is a 0, it just becomes a 1. And now once it's a 1, I know that this one will prevail until the next PGT. I look at this PGT, I have K is a 0 and J is a 0, which means no change if you look at our table. So this will remain until the next PGT. And at the next PGT, I'm actually setting J is 1, K is 0. So that is the set state, but I'm already in the 1 state. So I will continue in that state. Okay, so that's the set until the next PGT, where I have a 1 and a 1, and therefore I can toggle. Okay, if we had the SR flip-flop, this would be ambiguous, but with a JK, this is not. And I will continue to the next PGT until I find K is 1 and J is 1. So I just toggle again, and then I have my timing diagram. So you can see here 3 things or 2 things. Let me just go with 2 first. The first one is that you need the initial state. And in this case, it is given as 1. But if I give you a question, usually I'll state it. If it's not somehow stated, I will state it. 2, you need to know that even if the inputs change between any 2 PGTs, that effect or the input change, the input changes will not cause an effect at the output until the next active clock transition, in this case, which is the PGT. So I don't need to worry about what is happening between any 2 PGTs. I just need to look at the point of the positive going transition or the active clock transition, and the current states of the inputs at that time instant will actually determine the output. And then finally, you need to know your truth table. Okay, this is for the JK flip-flop. These truth tables are really easy because the flip-flops are few. So you just need to know, okay, if I have 1, 1, what happens? If I have 0, 0, what happens? And so on. And how do I set or reset? Any questions on this? Okay. Okay, if there are no questions, we can continue. Let us look at the clocked JK flip-flop. And here we are going to assume that Q naught is equal to 1. So really, this is the same question. I just set it using, I just want us to use the NGT. Okay, so you can see the bubble there, and even the clock symbol is on the NGT. So if it is initially 1, that 1 will prevail until that point when 1 and 0, when I get my PGT. So that's a PGT. I am looking for the NGT. So I'm looking for that point actually. The NGT comes when I'm at a 1 here and a 1. So I need to toggle. That is toggle. I'm going to use symbol T. And this will prevail until the next NGT. When I look at the NGT, at this point I have a 0 and a 0. So there will be no change. Okay, I can call it NC until the next NGT, which is this point. And I think if you look at this, it sort of goes there. It sort of goes there. So I have a 0 and a 1, and we know that that is going to set. By setting, I go to a 1. So that I'm setting, I go for the next NGT. And this NGT will take me, that is 1 and 1. I toggle until the next NGT. And this NGT, at this point, again, I have a 1 and a 1, and I toggle again. Okay, so I think, yeah, so these are two different, they are going to be different. You can see here with the PGT, the output is different from the case for the NGT. And so it is important which one you use. Usually I'll tell you which one you use anyway. But yeah, this is how we do it. We just look for the point at which we have our active clock transition. We look at the current state or the states of the inputs at that point, and then determine our output. So we have our other flip-flop is a clocked D flip-flop. A D flip-flop, actually D basically stands for data. And you're going to see that in a lot of our applications, when we are dealing with data, we tend to use the D flip-flop. For it, it's really easy. It has one input, okay, one data input, which is the D, and a clock. It's not similar to these others we've seen, which have two inputs together, two control inputs together with a clock. This one just has one data input. We call it D, hence the flip-flop, and we have the clock, and then we have our two outputs out of the flip-flop, which is the normal input and the inverted input. The truth table here is very easy. When you have a 0 at the output and you give a positive going to, in this case, it is a PGT, you're going to get a 0, okay? If you have a 1, you're going to have a 1. There is this switch making noise. I'm going to remove them since I don't know who they are. So, so you can see that the D flip-flop is so easy in the sense that what you have at the data input simply goes to the output, but it needs to wait for the clock transition because, again, this is a clocked D flip-flop, so it is synchronous. So you can see here, they are assuming that Q naught is a 1. So we have a PGT, okay? So you can see that we have a 1 here. At the PGT, the D input is a 0. So we just go to 0. At the next PGT, the D input is 1. So we come to 1. At the next PGT, the input is, okay, 0, 1, 0. So if we find a 0, it means we go back to 0, 1, 0. The next PGT, we have a 1, so we go to 1. The next PGT, we have a 1, so we go to 1, we stay at 1. The next PGT, we have a 0, so we go to 0, and again 0, so we go to 0. So what you have at the input simply goes to the output in the D flip-flop, but it is synchronized operation, so you have to wait for the clock. In this case, if we assume that still Q naught is a 1, this is an NGT. Okay, so this is for NGT flip-flop. We are going to have a 1 all the way to the NGT. Let me see. This is the NGT positions. In this case, your clock is actually rectangular. It is not square. And so we have a 1 and a 0. So in this case, it is a 1. So when we look at this point, it is a 0 actually. So we go to 0. We are going to remain at 0 until this point, which is now we go to 1, because the D flip-flop is at 1. Here it's at 0. The next NGT, we have a 1. No, we have a 0. So when we reach this point, we go to 0. The next one is a 1 and a 1. So that means we transition back to 1, and we remain at 1. And at this NGT, we have a 0 and a 0. So we are going to come down to a 0 and continue with a 0. Okay, so that, again, if you look at these two, they are different. And so once again, NGT and PGT do not necessarily give you the same output. They can, but they don't necessarily do that. Joseph, Doctor, why do we always start with 1, yet the output is 0? I don't know what you mean by that. What do you mean by that? Can you explain? What do you mean by we always start with a 1, yet the output is 0? I mean, we could have assumed that assume Q naught is a 0. It wouldn't make a difference because the operation would still be very much the same. And so, for instance, in this case, we would have, instead of a 1, we would just start at a 0, and our operation would actually now be like that. So our assumption at the beginning actually doesn't matter. And I think we talked about this in the sense that if you want your flip-flop before you start operating to start in a certain state, you just do something. You can either set it or clear it, and we are going to see in a moment in this lecture, in fact, that there are some inputs that allow us to do that very quickly. In fact, there are some arms up. Magaba, Jesse.
Yeah, I want to ask about what's the difference between ambiguous for the JK flip-flop and the toggling of the is it the JK?
The JK,
no,
the toggle.
Yeah, the toggle, and then the ambiguous for the, is it for the SR?
Is SR, yeah. So for the SR, you can see that we set using 1, and there's really no difference. I'm not going to give you a technical answer here. But when it is 1, 1, it means that you're trying to set and reset at the same time, and that's ambiguous. Now, the JK removes that difficulty, and in its internal circuitry, when you are trying to set and reset at the same time, for it, what it does is it toggles. So it is a way, it's as if the JK finds an acceptable way to deal with that ambiguous input combination of a 1, 1 by just giving it a toggle, toggling the output. There is no technical reason, there is no big reason why. That is simply how these two actually operate. So that, for instance, in the JK, once you have a 1 and a 1, you still know what to expect. But in the SR, when you have a 1 and a 1, you don't. And that's why we say that it is ambiguous, it's invalid, and it should be avoided, because you don't know what your output is going to be. It could be either 1 or a 0. And if you don't know if you cannot predict your output in digital circuits, then obviously you are doing nothing. Daphne, you had the question? Daphne Kabago.
Excuse me, sir. Good morning.
Good morning.
I was just requesting for a re-explanation on the JK flip-flops.
Okay. Yeah, I can do that. I can do that. Caroline, I beg your pardon on how the JK flip-flop operates. So there is also Caroline. And can you please redraw the timing diagram for the clocked D flip-flop? Okay, so that one is for the D flip-flop. So basically, Kamoga, so basically there is no invalid state for the output. Yes, for the JK flip-flop, there is no invalid state, that is true. Okay. So let me try and create a new diagram. Okay, so I'm just going to use this one for those of you who didn't get the JK flip-flop. So we have a new JK flip-flop, okay? In fact, we are going to look at two examples. Here we are going to look at NGT and PGT. Let us start with the PGT, which is actually the previous example. We have our truth table here, so that makes it very easy. And so you need to remember these truth tables. I'm not going to give them to you. When it is 0, 0, it is no change. So in that case, it is similar. In these first three instances, it is similar to the SR. Because when you have a J as 1 and a K as a 0, you're trying to set. That means you're trying to make a Q 1. When you have a 0 and a 1, you're resetting. And the difference between the J and the SR is that in this instance, you toggle, okay? In the other case, it's invalid, it's ambiguous. You don't know what will happen. Here, you know what will happen, which is the toggle, which means that if you add a 1, you go to 0. So let us assume here that Q naught is a 0. Let's start with 0 since somebody asked a question about this. So we are going to do PGT first. Q naught is 0, meaning that you have a 1 here and a 0, that's Q. And it means we are going to be in the Q until the PGT, right? That PGT should tell us what should happen next. And at this PGT, we look at the current states at the inputs. The inputs are J and K. So K here is a 1 and J is a 0. If you come to this, this is that state, 0 and a 1. So that means that if we have a 0 here on the J and the K as a 1, we get our output is 0, but here it's already 0. So it will continue as a 0 until the next PGT. You can see that actually in between here, J changes. Yeah, that's okay. J changes, but I'm not so concerned until the next clock. That is why we say that these are synchronous systems. And so yes, your inputs can change, but the effect they are supposed to cause will not happen until the active clock transition, in this case a PGT, does actually happen. So at this point, I again look at my J and K, that's a 1 and a 1. A 1 and a, actually, so that is clear. So I can say reset. A 1 and a 1 here will give me a toggle, okay? If it was SR, this would be invalid, so ideally we shouldn't have this, but this is JK, so we toggle. By toggling, it means we have a 0, we go to 1. So that means here, I go to 1, and that's a toggle. By the way, you don't have to write these words below in your timing diagram. They are not necessary. I'm just writing them just so that, you know, as a teaching thing, but you don't have to write them. And I would say don't write them just so that everything remains neat. So once I know that I'm in 1, I know I will stay in 1 until the next PGT. In this case, the next PGT, I find that my inputs are actually now at 0 and 0. Okay, 0 and 0 is no change. So I will stay at 1. At 1, I have a 0 here and a 1. A 0 and a 1, that's the 1 in the set and a 0. So this is the input. 1 at J and 0 at K actually sets the flip-flop, but I'm already in the 1 state. So I will stay in that 1 state until this PGT where I have a 1, a 1, a 1 and a 1 in my truth table gives me a toggle. So this is toggle that was set, that was actually no change. And I will remain in the 0 state until that point where I can see it's a 1 and a 1, a 1 and a 1 once again gives me a toggle. So I will toggle to that. Okay. Now, let us look at the NGT. I'm going to rub off these ones. Okay. What if we were doing the NGT? If we were doing the NGT, we can start with our Q naught is equal to 0 or 1. Really, this doesn't matter. Let's once again do a 0. And I'm just going to draw it down here. Q 1 0. In this case, this is NGT. That was PGT. In NGT, I'm not interested in this. I'm now interested in these. Okay, in these transitions. These are the NGTs. And so I'm looking at, in this case, B, D. The next one is F, H, and J. So if I start at 0, if initially it's 0, it will be 0 until I get my first NGT. My first NGT, I find that actually along here, I have a 1 and a 1. A 1 and a 1 means I toggle. So if I was at 0, I will go to 1. That one will prevail until the next NGT, which finds that I have a 0 on K and a 0 on J. So that will be no change until the next. This is no change. This is toggle. Until the next clock transition, the active clock transition. In this case, I have a 0 here and a 1. So a 1 and a 0, a 1 at J and a 0 at K, I'm setting. So that's set, but it is, it will stay as a 1 until this point. Where I can check again, and I believe we have a 1 and a 1, which means I toggle. If I was at 1, I toggle to 0 until the next clock transition, which is once again a 1 and a 1, and I toggle again. So this is how the JK flip-flop works. For those of you who had not got it, I hope that Daphne and Caroline can give me, you can just text here and say you've got it. Does the word toggle mean a change from a 1 to 0? Or yeah, so toggle means that if you are in a 1, you go to the 0. If you are in 0, you go to 1. Now, the D flip-flop is actually the simplest. Okay, the D flip-flop is that simplest. What you have here, we are not combining things, because you see with the JK, you need to look at what the J is and the K is. Here we are not comparing things. We are just saying whatever D is, it will just go to the output. If it's a 1, you have a 1. If it's a 0, you have a 0. So here you can see that they've assumed Q naught to be 1. So you're looking for PGT, so it's still clocked. And at this point, you see that D is a 0. So you go to 0. At the next one, D is a 1. So you are at 0, you just go to 1. At the next PGT, D is back to 0. So you also go back to 0. At the next PGT, D is a 1, and the next one is a 1. So you have a 1, and this point, you still have a 1. Here you have a 0 and a 0, so it's just the same, but now you are dealing with just one input. And so you will remain, you just see what is at the D, you just put it at the output Q. Okay. Okay, so I think we can move on. Let us look at how we implement the D flip-flop. You can actually implement the D flip-flop using the JK flip-flop, as we can see here. If you have the JK flip-flop, you cannot say, but I need to use a D flip-flop, because actually you can manipulate the JK flip-flop to create a D flip-flop by doing what? By having your D input into the J and an inverse of that into the K. So you get the same data input, you put it into J and you get its inverse. You can see this inverted inverter, you put it in the K, and we are going to test in a moment if this is the case. Musa, I think you have a question. So once Musa has finished talking, we can talk about that. Please go ahead.
Yes, good morning, sir.
Morning.
Good morning, doctor.
Good morning.
Okay, my question is about, say we have a clock JKFF, maybe PJT. Can we have a scenario where we have where we can have maybe J and K are making a bridge Like, can that scenario be there? And if it is there, how can we deal with that? Maybe we
Where
are at the
J and K are
maybe
making
we
a
are at
bridge.
a bridge, yeah, or spike.
I don't understand your question. Do you mean what kind of bridge?
Like the J is coming to low, at the same time the K is coming to high.
Okay. You mean like at the same time this is going
Yeah.
low? Maybe that is.
Yes. Yes.
Okay.
And at that point we have a what? A PJT maybe, and we want.
Yeah, and at this very point we have our clock transition.
Yes. With that scenario there, and
it is there, but it is very rare, and I wouldn't usually give you a confusing scenario like this. Obviously, when you're doing this on scale, it is very easy to visualize it, but in real life, you think that because these are things that are happening over nanoseconds. Nanoseconds is like 10 to the power 9 of a second. So it's very difficult to find a scenario where in that very instant, two things are changing and also the clock is coming. If at all they happen, if at all they happen in that way, the first one that beats the other one to the 50% percentile, in other words, the first one that makes the transition fast will actually we change the output, and then but the next one will, so it at some point what I'm trying to say is that something must happen first. However, if that scenario happens, I don't really know what would happen. I just don't see it happening in real life. It's just the margins are too small for us to worry about a scenario like this. But in our timing diagrams, I'm not going to give you something confusing like this one.
Okay, sir, thank you.
Magaba, do you have a question? Or is this a hand from before?
Yes, I have a question.
Okay.
Like, how do we determine our true output? Like, do we have to cram it, or I don't know?
Do you mean by Q output you are really saying how do we have to cram the truth table? Is that what you're saying?
Exactly, something like that. No, like for the JK.
Yeah.
Like when it is 0, 0, when J is 0 and K is 0, then you say that there's no change.
Yeah.
But then for the DFF, like when it is 0, the bund will remain 0, like the Q. So
yeah,
how comes that it is 0, not 1?
But it is what you are telling me here. It's these are different flip-flops. Let me just break it down for you. This I don't cram this. I don't really think you should cram, because we are not going to be working a lot with a NAND gate flip-flop, by the way. But let us look at the SR flip-flop. All I need to remember is that S is equal to 1 sets. Okay, for the NAND get, S is equal to 0. You remember that this would be our set. So once I know that S is equal to 1 sets, and then I know, and then really once I know this, I can work out the rest, because I will know that by extension R equals 1 will clear. That means S is equal to 1, R equal to 1 shouldn't happen. Okay, it is ambiguous, it is invalid. And then if I know that S equal to 1 and R is 1, if I know that S is 1 sets, then it means also that R is 1 also sets, meaning that these two reside in the 0, 0 states in general. And then I know that S is equal to 0, R is equal to 0. This is in their inactive states, no change. As simple as that. When it comes to JK, I know it is similar to SR with toggle, and toggle applies to the ambiguous state. The rest is the same. I'm only removing the ambiguous state and adding the toggle state instead. And then with the D flip-flop, what is at input? Okay, I can say input equals output. but with a synchronous operation, of course. All of these have synchronous operation. So what I'm seeing at the input goes to the output. Whether it's a 0, it goes to the output. If it's a 1, it goes to the output. And that is the simplicity of the D flip-flop. The other thing is that the D flip-flop only has one data input. The other one is the clock. So I don't think we need to cram this. And if you need to cram, you should only cram one line, basically. One combination of states. So another thing is that once I know, for instance, that 0, 0 causes no change, that's enough. Because if 0, 0 causes no change, I know that this is where, these are the states where the two inputs reside normally. And it means that they will set or reset, or in other words, they'll become active if they go to 1. And if you're making them active at the same time, that is ambiguous for the SR, but it will be toggle for the JK. So yeah, so I don't think you need to cram this. You just need to do a bit of reading and be able to remember how, at least how the JK operates. JK has toggle, SR does not have toggle, and the D is just simply very easy. Yeah, okay. So let us look at this. I mean, the other flip-flops are made of combinations of gates. I am not going to answer that. You can go and do some bit of Googling and find out. Okay, so let us look at this. So here we have J. Here we have K. So in a D, our J, if D, we can have D, because if it is 0, it means K is 1, right? And if D is 1, it means K is 0. Do you notice that in this truth table, once we have this, we just have these two inputs, because J and K can never be the same. Since K is being fed with an inverse of what is fed to J. So this is all we need. If J is 0 and K is 1, and remember these are D inputs. If J is 0 and K is 1, we clear, which is 0. If J is 1 and K is 0, we set, which is 1. But actually the input at J is D. So you can see that this input simply comes there, and that input simply comes there, which is the same as the truth table of the D flip-flop, DQ 0, 0, 1, 1. So I think you can see that these are the same, really. So you can have your JK flip-flop. If you connect it in this way, you will have created a D flip-flop. What happens in the timing diagram for SRFF when SR? I don't know, Dembe, Oscar, if you attend classes, but I've probably many times said that in the SR flip-flop, this state would be ambiguous, and so you're not going to find it in the timing diagram. Okay. So we have some of the operations of these flip-flops, including data transfer. We have parallel data transfer and serial data transfer. This is a scenario that shows you the parallel data transfer. We have some combinational logic circuit that has 3 outputs, X, Y, and Z, and X is being fed into the D flip-flop, Y into another D flip-flop, and Z into another separate D flip-flop. However, you should see here that D flip-flops, the 3 D flip-flops are clocked simultaneously. What I mean here is that they are clocked by the same clock. If you notice here, you have a clock signal here that is NGT, and it is feeding that clock input, and that clock input, all at the same time. By the way, when we arrange our flip-flops in this combination, we call them registers, but I'm going to talk a bit more about that. So what does this mean? It means that all these flip-flops will be triggered simultaneously, okay? Triggered together. By triggered, I mean together. By triggered, I mean that they will receive their active clock signal at the same time, and the trigger is, that is a trigger because it tells it, okay, you can change the output based on the current states of the inputs. So you have this clock signal, which we can call clock, really. You can have clock, you can have transfer with a bar. However you write this is fine, but we already know that it's an MGT. You have a bubble here, and so on and so forth. Now, if I get my, okay, so if I have my input X, Y, and Z, let's assume that X is a 1, Y is a 0, Z is also a 0, okay? These are coming from the combinational logic circuit. And that means this 1 is saturating all the way to there. This 0 is saturating all the way to that point, and another 0 saturating there. If I get my get clock signal, you know, if I get my clock signal, what happens? Can somebody answer that for me? If this is the state at the inputs of the D flip-flops, 1, 0, 0, when I get my active clock transition, which is the NGT, which actually triggers all the 3 flip-flops simultaneously, what will happen? Anyone wants to try? Ntambi, Isaac, Sajawaza, Ntambi, what would happen?
Pardon the question.
You didn't hear the question. Well, then am I not audible enough? Magaba. Magaba, Jesse. Okay, Charles. Kafluma.
Yeah, for me, I think when the clock is in, the outputs of all the D flip-flops will be high. That means it will output X, Y, Z at the same time.
But what are the outputs of X and Y and Z? Okay, so anyway, you remember that we said that for the D flip-flop, when the active clock transition comes in, what is at the input goes to the output. So when you get your NGT, this one transfers to that point. This 0 transfers to that point. It's really not transferring to that. It's like the state changes. What was at the input simply goes to the output, and this 0 would go to Q3. So you have your 1, 0, 0. And this is the new state. So in other words, we have transferred data from this combination logic circuit into and stored it into these 3 flip-flops. And I said when we consider them like this, we call them registers. A register, you know a register in your high school is where they write names, and so it's like a storage. So registers are actually what we call memory devices that those like when we store a word, like a 4-bit word, we store it in a register, and a register, in that case, a 4-bit word is stored by 4 flip-flops. So that creates a register, a 4-bit register. Now, somebody might ask, what happens to the states, because you could say that initially maybe the states were 1, 1, 1. Now, if we've pushed this 0 to that position, where has this 1 gone? In fact, 1 has been flushed out. We are going to see later on how we can transfer information. So the information that was at 1 has been flushed out along that line. And if you had another flip-flop here, then this 1 which was here is now, in fact, inside that flip-flop. We are going to study this a bit more, but this is one of the major applications of flip-flops. They sustain or they facilitate data transfer. They do this both for serial data transfer and also for parallel data transfer. Any questions? Charles, do you have a question? Your hand is up.
Sorry, I forgot it up. I'm sorry.
It's okay. So let us look at the D-latch. This D-latch is based on the NAND gate latch. You remember the NAND gate latch, which is a flip-flop? This is also a flip-flop, but we call it a D-latch. It is also, you can also call it a transparent latch. Now, it is created using some sort of D flip-flop. So you have your data in. Let us look at the circuit the way it is. We have our data in. You can see that the set and the reset are R is equal to S are active low. Okay, so you remember the NAND gate latch. This is obviously a NAND gate because that is basically similar to that. Okay, so let us see how this operates. This is not edge triggered because this is not edge triggered, so it's not clocked, so to speak. Let us see how this would operate. Let us say that EN, the enable input, is a 0. If the enable input is a 0 here, the moment you have a 0 and a 0 here, it doesn't matter what D is and D inverse is, our reset and set will be a 1 and a 1. I think you remember how the NAND gate operates. So you have S, okay, let's say A, B, Q. This is the NAND gate. 0, 0, 0, 1, 1, 0, 1, 1. So that's a 0, 1, 1, 1. That is how your NAND gate latch, the NAND gate works. So the moment you have a 0, you can see all these combinations that have a 0, the output is a 1. And when the output is a 1, that is irrespective of what D or D inverse in this case here is. So once the outputs are 1, you are not setting or resetting, since these two are both inactive states of the set and reset. So you can see here we say that actually the D does not matter. This X means don't care, and we've done don't care states. As long as your enable is 0, there will be no change. There is no change because you're neither setting nor resetting. We can only have a change if we set the flip-flop or if we reset the flip-flop. But what if enable is 1? If enable is 1 happens, things change. If enable is 1 here, the D can be 0 or 1. If D is 1, sorry, if D is 0, let's look at that case. If D is 0 and enable is 1, so you have, in this case, you will have a 1. Obviously, here as a 1 as well. A 0 and a 1, you'll have a 1. But this D being 0, here it will become 1. So you have a 1 and a 1, giving you a 0. And when you have a 0, you reset, meaning your output will become 0. Okay? And the other way is if enable is 1 and your D is actually 1, if D is 1, that means D inverse is 0. You have a 1 here, so you have a 1 and a 1, meaning your output now becomes 0. 0 and 1 here, you'll become, your output will be a 1, meaning that actually we are setting. If we are setting 1 and 1, our output will be a 1. So this is called a transparent latch. And this is the reason why it is. You can see that when enable is 0, we do what we call latch. A latch is like you keep it in that same state. Okay. But when D is equal to 1, so when enable is equal to 1, the D input goes to the output. You can see that for these states, 0 will go to the output, 1 will go to the output. And so we say that when EN is 1, the latch, the D latch is transparent. Right. The D latch is transparent. It's transparent because the D input is going right through. Another thing we should remember about this is that enable is actually asynchronous. This whole thing is asynchronous, no synchronism. Okay, so we are not clocking or anything like that. And if we look at this, we can see that whenever enable is 0, our output is 0. You can see when enable is 0 and we don't care what the D is, we have no change. In this case, they had assumed that Q is equal to 0. So because we have no change, if here we have our 0, the Q will be 0 because that is the initial state. But now when enable changes to 1, that is the transparent state. So Q becomes similar to D. And because D is a 1, our Q will now go to 1. When this state here is the latch, this is the latch region. And here the output will be no change. So no change, you see. So no change. So because we are at 1, we just stay at 1. And in this case, when enable is 1, this is transparent, the transparent region. And you can see that the D will now pass through to the output. And then in this case, it is latch. It doesn't matter what D is, it will just be 0, which is no change. So this is just a small difference for the D flip-flop, meaning that you can actually create a latch, a transparent latch, instead of a synchronous or clocked flip-flop, D flip-flop. You could say, yes, you can say that enable is a control input, because as you can see, it is the one that makes your flip-flop either transparent or latched, or non-transparent, so to speak. Okay. Okay, so before we continue, I want us to have a short break of 5 minutes. We'll start at 11:01. I need to take a little some water. So please, you can go and have some water also, but don't be long. I'll be back in a short while.
Anybody disable.
Okay, I'm back. And I think Shakira, that guy, had said I pardon. So I imagine that she meant this thing. So with this one, and if I can, go back to what I think Magawa said, how do you record this? This is not something I would say cram. Actually, I don't encourage you guys to cram in this stuff, because in digital electronics, I mean, how much stuff will you cram? There's just so much. So you really just need to understand. So if I were to set something like this, I would probably not set it in a way that I want you to be able to record this truth table. I would probably give you this whole circuit, and then you can create the truth table. So what I wanted to, if I can just recap on this one. Ivan, I'm not too fast. Actually, I don't think I'm too fast, but thanks for the feedback. Maybe usually when I say, have you understood? And you do not say you've not understood. You do not say you've not understood. No, yeah, something like that. I'll ask you, so any questions? If you have a question, I'm really just saying, have you understood? Can I move on? I cannot give you a minute for you to think about if you've understood or not. So it is that point where you tell me that maybe reply or maybe restate this or explain this or something like that. Otherwise, when somebody is online, they can just keep moving and moving and moving. Batamye Abudur, Batamye, maybe you would state it that way. Joel, how do transparent to latch with an OR gate? I think you can. You should try and work it out. I think you can. There's no reason why you can't do that. Excuse me. The circuit wasn't complicated, but I am going to do that. That's okay. Let us look at this one more time. This is called the latch, the D latch. So it is like a D gate. It is like the D clocked gate. Sorry, not D gate. It's like the D flip-flop, but this is a latch. The D flip-flop is edge triggered. If you remove the edge triggering, that means you're removing the clocking, you end up with a D latch. Removing the clocking, and you set your thing like this, you're going to end up with a D latch. And this is how it happens actually. So the enable, when enable is a 0, if you have a 0 here, if you have a 0 here, it does not matter what is at the D or D inverse. Remember, this is D inverse. Because you have a 0 here and a 0 here, we already know that this will be a 1 and a 1. Because we know how the NAND gate, the NAND gate, if you don't remember these truth tables, you are in trouble. X 0, 0, 0, 1, 1, 0 here, everything is 1, and then 1, 1 is when you have 0. So if you have a 0 and a 0 here in these first 3 states, you're going to end up with a 1 and a 1, and that is irrespective of what D is. That's why you see I'm not looking at these two arms. And once you have a 1 and a 1, you cannot set or reset because these two are active loss. So you are not setting or resetting. That's why you have a 0. This is X, you don't care, and that's no change. No change means it stays in the same state because you are neither setting nor resetting. Now, let us look at the other scenario, and I'm happy to rub out this. The other scenario is when enable is 1. When enable is 1, it means you have a 1 here and a 1 here. If D, in this case, D can be 0. If D is 0, you have a 0 here and a 1 here, because obviously that will be an inverse. A 0 and a 1 will give you a 1. A 1 and a 1 will give you a 0. If you look at that. If we have a 0 here, we are resetting. and the one here we are not setting, so that's okay. So that means that if your D is 0, we are resetting, making this Q 0. So you have, if enable is 1 and your D is 0, your output will be 0. So you can see it's like, it's still a D, it's called a D latch, but you can see that the D input has passed to the output. If D was a 1, that means D inverse is a 0 here, and you have a 1 and a 0, now you have a 1, but 1 and 1, now you have a 0. And when you put a 0 here, you're setting. That means when your D is a 1, you set this flip-flop to its output being equal to 1. So once again, we can see that 0 will give you 0, 1 will give you 1, but only if enable is 1. And this is the state we call, the range we call the transparent state of the D latch, or transparent range or region or something like that. When enable is 0, that is latch. We latch, so it is latched to that same state, so to speak. There is no change, and that is irrespective of what D is. So if D was a 0, it will stay 0. If D was a 1, it will stay a 1. And then we get to this this timing diagram. We have been told that initially Q is equal to 0. So for the regions where enable is equal to 0, we know those are latch regions. The state will remain the same. When you have 1, these are transparent regions. Transparent regions. What means by transparent? It means that what is at the output, at the input of D, will go to the output. What is, if it's 1, it's a 1. If it's 0, it goes to 0. So here, the transparent latch, you know, what is at the D input will go through to the output because enable is 1. But before that, when enable was 0, you can see that D is a 1, but actually the output will remain latched to a 0 until we have the transparent region. So that D will go through to the output. At this point, we have this region, which is the latch region. Latch means no change. So this one will prevail until that region is over. And then we go into the transparent region, and you can see that actually now the latch is transparent. The D input is going to the output. And that's why you see this is very similar. In this range, the D is actually at the output. And when enable goes back to 0, we again have our latch, meaning that the D is not going through to the output. We remain latched to that state. And I think, yeah, I think that's that really. Okay, thank you, Shakira, for letting me know. Let us look at asynchronous inputs. Thus far, we've been looking at synchronous inputs. And synchronous inputs are those inputs. They are the control inputs that have to wait for a clock to operate. Asynchronous inputs just change the output at whatever point. Once they are applied, they change. So in this case, they are like combinational logic circuits. They just change. Yes, Musa.
Yes, doctor. My question, like, okay, right. My summary, which I made in my head, is like, for a D latch,
Yeah.
should I say that if Q is 0, sorry, if enable is 0, Q is 0, and if enable is 1.
If enable is 0, Q is no change. So if it's 0, it remains 0. If it's 1, it remains 1.
Okay, and if enable is 1, then Q is D.
Q is D, yes, exactly. So you could reduce this and say, you know, enable D and Q. And you say if it's 0, Q naught. And if it is 1 and D, then you have D. So this truth table is also what? Is also correct. Okay. Magaba?
So how would you see I don't care state on a timing diagram?
No, you don't have a don't care state. it doesn't mean that it is not a state. It is still a state, you just don't care about it. So for instance, in this case, when enable is 0, we don't care what D is, this thing will remain as is. Even in this case, you can see that when enable is 0, we don't really care what D is because we already know that the output will remain 1. It's a no change. So you can see the input is changing, but that doesn't cause any change on the output. So the don't care state will actually be a state. We just don't care about it. But anyway, it's an input state. So you usually be given that. You don't have to, you won't have a scenario where you're creating input states, unless of course, I ask you to draw a truth table and so on. I'm going to show you how I can ask a question about a truth table. Okay, so the asynchronous inputs are those that operate independent. In terms of flip-flops, these operate independently of the synchronous clock and clock inputs. They don't wait for the clock to happen for them to perform the function that they have been, they usually perform the active function. In that way, they are like combination logic circuits where if you change the inputs, they will create the expected change at the output. So in terms of flip-flops, our override inputs are the preset and the clear or the reset. Now they can be active high, but they are usually active low. And so that's why we usually have something like that. And actually they can also be written as pre and CRR. So preset and clear. That should be very easy for you to remember. That preset, you can also have that. Sometimes you'll find pre and clear with no bar. It means that actually once you have active low here, after the bubble, you have like active high because that bubble shows like an inverter. Anyway, so these ones operate the moment they are asynchronous inputs in the sense that they will not wait for the clock. Once you set them, they will just operate. Now the preset sets the flip-flop and the clear clears the flip-flop. So if you want to make sure that your flip-flop is in the one state, you can just preset it. Preset. It's like before any operation, first preset or first clear. So if I want to make sure that, okay, I'm going to do some data transfer, but I want to make sure that my flip-flop is initially 0. I just set it, I just clear it. If I want to make sure that it is in the one state, I can preset it. How do I preset? Just to preset, just make sure that pre equals 0. And to clear, just make sure that clear equals 0. That means that they usually reside in the one states, 1, 1, but they are moved to 0, which are the active states, either to preset or to clear. Another thing is that we call these override inputs. They are override inputs, but because actually they override the synchronous inputs. So the asynchronous inputs in this case will override the synchronous inputs. Let me find a case where, for instance, I say that J is 1 and K is 0. Okay, here I know that I'm setting, but also my clear is 0. In this case, actually this would give me my output as Q naught. No, as Q equals 1. Okay, my output would be 1 because J equals 1, K is 0 actually sets the flip-flop. But in fact, what happens is that this whole combination, by having all these 3, actually my input will remain 0. The reason why it remains 0 is because my clear is still 0. If my clear is 0, it will override whatever the synchronous inputs are trying to do. Okay, so that's why we call them override inputs. Isaac. Okwir Isaac had a question. So let us look at this truth table. Let us look at this truth table. So we already know, you can see that I've already said that pre is equal to clear equals 1. This is the normal condition. These are the normal states. In other words, you don't want to do anything here. So just keep them as PRE, pre is equal to clear is equal to 1. Then they won't do anything. They won't clear, they will not preset. So you can see that this state, this range is pre equals clear equal to 1. So then when this is the case, then your asynchronous inputs will operate as we expect them to. So you have J is 0, K is 0. That should be no change, but it is an NGT. Okay, so you have your arrow going down there, and you have no change, Q naught, sorry, down here. If it is 0, 1, you're clearing, so synchronous reset. Okay. It means it is synchronous reset because you can also set asynchronously. By resetting asynchronously, sorry, you use the clear. But because here we are resetting using a 0 and a 1, these are synchronous inputs, they've called it synchronous reset. But if you just said reset, I would give you, or clear, I would give you the mark. 1, 0, you have synchronous set, and 1, 1 is the toggle. So you sync toggle, synchronous toggle. Now we have this state where we have this is the asynchronous. Obviously, this is the synchronous, asynchronous operation, something like that. If I have a 1 and a 1, no change of active state of the clear. So asynchronous now, asynchronous clear. If it is a 0 and a 1, asynchronous preset. Okay, that means I set my output to a 1. And then 0 and 0 is invalid. It is ambiguous because you are trying to preset and also clear at the same time. So that takes us back. Now you can see that when this is happening, J equal to K equals we really don't care. Whatever they are, as long as we are setting or presetting, as we saw in this example down here, J and K do not mean anything once we are either clearing or presetting. So that's why they are all X's, because once one of these is in the active state, the states of the J and K do not really matter. Obviously, there is this state, because in this state, we have a 1 and a 1. This is the only state I have a problem with. If we have a 1 and a 1, we are neither presetting or clearing. So actually, these really mean that. So this whole thing is that asynchronous. In other words, if you have a 1 and a 1, then you have the synchronous operation. Is that clear? Okay, so I could, okay, so Ivan, I don't know if that is fast, but I think, yeah, I think that this is the truth table. Now I could bring a truth table like this in the exam, where I say that you have J, you have K, you have clock, you have pre, you have clear, and you have Q. Oops, my lines are not the best. I don't know why. Let me just insert a new slide. Okay, so you have J, K, clock, pre, clear. We have J, we have K, bear with me. And then I have Q here. And I could have a number of lines. And maybe a number of lines. Okay, so let's say I have a 0 and a 1 and a 0 and a 1 and a 0. And I leave that. And I have a 1, 1, 1, 1, 0, 1, 1, 0. Okay, so I could have that. I could give you that and I ask you to complete the truth table for me. And so, I mean, okay, that's a 1. So then where do you begin? Okay, so you need, first of all, tell me what the clock transition is here. So let's maybe say PGT, so you can fill that in. And we know that a 0 and a 1 with a PGT where these are not active is actually synchronous clear. Okay, J0K is 1. This will be synchronous set. Okay, this is synchronous clear or reset. Now here, because pre is 0, you know, because pre is 0, it means we are presetting. So we have a 1 there. Or that's a 0, that's a 1, and we have a 1 here. And this is a synchronous set or preset. Because it's a 0 here, this wouldn't matter. So you need to be able to realize that these are don't care. Anything else you put, you're not going to get any marks. And if they clear these two, we said they are override inputs. So if they are overriding the other things, once they are active, they override the other ones, meaning the other ones do not matter. And so if you have a 1 and a 0 here, you are set, you are clearing, which is asynchronous reset or clear. And again, you have to realize that these are active. Sorry, those are actually don't care states. So you have got to be able to realize that that is don't care state. Okay. So I hope that that is also clear. Doctor, does the preset and clear always work as an AND latch? I don't know what you mean. No. I think maybe now I understand. Do they always work as an AND latch? No. These, all the flip-flops have them. Any flip-flop, even the D flip-flop. Let's say we have a D flip-flop. And this is D. You have a clock. And you have Q and Q naught, Q inverse, sorry, not Q naught. You always have these. This is clear and this is preset. So actually, the actual symbol, the full symbol of our flip-flops always include clear and pre. This should not be here, it should be here. And pre. And then you can add your inputs, maybe J, K, clock, Q inverse. In other words, all our flip-flops are able to have an asynchronous reset and an asynchronous clear. It's just that we don't usually show them, but we need to remember that they are always there. We just don't show them, just keep the diagrams a bit cleaner and neater and more concise. But we need to remember that these all flip-flops always have a preset and a clear signal. Chichoncho Christopher, how do you determine whether the arrow of the clock goes up or down? So I've been teaching this so many times. I think maybe you missed some lectures. So a clock going up shows a PGT and a clock going down shows an NGT. So you need to know what you are dealing with. So now in this case, it would actually be up. I was just saying that in the case of this, I mentioned it that let's assume a PGT. Okay. Yeah, I don't know why my throat is a bit dry. I think I've overtalked. But I have a small glass of water here, so we will be able to push to the end. Danielle, do you specify that or we base on some principle to find out? What do you mean specify? No. I've explained how you can know what a PGT is and how an NGT is. There are three signs. The first one is a bubble at the clock signal. The second one, usually they'll draw some kind of pulse and show you whether the arrow is. And thirdly, you can also tell from the symbol of the clock. So if I draw my clock and I put a bar, already automatically that is an NGT. If it is just CLA, K, and there is no other thing to show you that it is a PGT or NGT, then this makes this a PGT. Okay. So let us look at this example. This example, of course, there is an answer. I've just redacted it just so that we can explain. So yes, this is actually the actual flip-flop symbol. It has your inputs, the synchronous inputs. It has a clock. It has these two asynchronous inputs, one for presetting and one for clear, and your two outputs. All flip-flops are like this, but usually don't show these asynchronous inputs because we actually don't usually use them. We only use them when they are needed, like usually at the beginning of the operation. And so usually when we draw flip-flops, we don't show them, but we need to remember that they are always there. So in this case, they've shown you that J is equal to K is equal to 1, always. So that means that for synchronous operation, we always toggle. Since J and K have been kept to 1, it means that every time we get the right clock signal and we have synchronous operation, we are going to toggle. We need to remember that asynchronous operation overrides synchronous operation. And also that the asynchronous inputs override, obviously, the synchronous inputs. So let us look at this. And of course, you can see that J and K have been connected to a 5V input, VCC. So yeah, there's J and K. Then we have our clock. Now here, this is what I was saying. You can see from the bubble, you can see from that this is actually an NGT. So it is like that. So you come to your clock, you're looking for NGT. This is where luckily they've drawn things for us. Another thing we can say, what is, I don't know what, we can assume that Q naught is equal to 1 initially. Let's assume that it was initially 0. Maybe we preset the flip-flop before this time. So Q1, 0. So that means Q is 0, sorry, Q is 1. It will remain 1 until the next PGT. But before, remember, we were doing it like this. We were not taking care of any other changes. But here we have to be careful because there is the preset and the there is the preset and reset, which are asynchronous, meaning that if they happen, they would cause a change immediately. We wouldn't have to wait for the active clock transition. So in this case, we can see there is that all of them pre and clear are 1, 1. So 1, 1 means they are inactive. So at this point, we look at our NGT. Our NGT happens at that point, and at that point, J and K are 1. So we should toggle to a 1, to a 0, sorry. We were at 1, so we toggle to a 0. Now, at this point, we preset. So when we preset, this input overrides the clock. In other words, this is an asynchronous input, and so it will override all other inputs, meaning we actually preset, meaning we go to a 1, right? So we go to a 1, and we can see that actually when it goes back to 1, you know, we remain in 1, obviously, until the next NGT. At this NGT, we see that, of course, our J and K are still 0, but our pre and clear are 1, 1, meaning that they are inactive. So we can toggle. So here we toggle, here we preset, then here we toggle again. And we are going to toggle until the next NGT. where we actually toggle again. Now at this point, we meet a clear input, and a clear input is asynchronous. So at this point, we are in a 1, we are going to be cleared back to a 0 until the next NGT. You can see that at this NGT, we would toggle again. Actually, here I should say reset. At this, we would toggle again, but we cannot toggle because we are still clear or reset, so to speak. So at this point, we are going to remain in the clear state. Remember, we would have toggled back to 1, but the clear state is still 0. So it will override that command and we remain in the clear state until the next NGT, where both of these are 1, 1, meaning they are inactive. And then at this point, we can actually toggle. Okay, so Semaganda Raymond, I'm going to repeat this for you. Let us look at this again. Okay, this is a new, maybe before we look at the answer, let us redo this slide one more time. It is very easy if you pay attention. If you pay attention, it's very easy. Once again, we know that by keeping j equal to k equal to 1, it means that we will toggle for synchronous operation. But remember, now here we have some asynchronous inputs. So if our Q is a 0, for example, let's now say for Q, let's still keep 1, meaning 1, 0. It means if it was initially Q naught is 1, we will remain at 1 until the next NGT. This is where our NGTs are. We are not interested in PGT. We are only interested in NGT. So we are going to be at NGT until this position. Our NGT shows that we need to toggle because J is equal to K is 1. We toggle, but at that point, we meet a preset. So because we are at 0, that's toggle, we meet a preset command, and the preset command is asynchronous and it overrides the current input. It actually overrides the clock. So the preset pushes us back to 1 because presetting means 1. We are going to remain here. We preset, I've put a P. We preset and we remain preset until the next NGT. The next NGT finds that at that point, preset is 1 and clear is 1. They are both 1, 1 means inactive because they are active when they are zeros. So 1, 1 means no change essentially, but no change in the asynchronous sense. In the synchronous sense, we see that J and K are still 1, 1, and so we toggle. Okay, so here we are going to toggle to a 0 state, and we remain in that 0 state until the next toggle, because we can see that here J preset and clear remain 1, 1, meaning no change once again. They are not changing the network. We toggle here until that point, but at this point, we get a clear state. A clear is asynchronous. This clear, this is an asynchronous state, and clear says our output should go to 0. So our output should go to 0 until the next NGT. At this NGT, we would normally toggle, but clear is still 0. And we have said clear will actually override anything. So at that point, we would otherwise toggle, but we continue in that state. Here, clear goes back to 1, meaning that we will remain in this state until the next NGT, which is 1, 1. Sorry, which is here is a 1 and a 1, meaning no change. But here it's also a 1 and a 1 for JK, which is toggle. So here we toggle back to 1 and so on. So this is toggle, that is clear or reset, and so on and so forth. And you can see that that is essentially what we have. Here we are going to toggle, but immediately we toggle, we find a preset command. So we preset, we go back to 1, and it happens immediately because this is asynchronous. We go to 1 until C, where we actually toggle on the NGT, and D, where we toggle again on the NGT, because remember J and K are 1, until E we are going to clear in that moment, since this is an asynchronous command that overrides. Until this point, at F, we would normally toggle will remain cleared. Until the next, and so you need to with this, when we are looking also at the asynchronous inputs, you're not considering only synchronous inputs. You're looking at JK, but you're also keeping an eye on preset and the clear steps. Okay. If there are questions, please let me know. If there are no questions, we can continue. We still have a bit of time. So those are asynchronous inputs, and we are going to be using them in the next few classes, but rarely. We don't usually deal with them because most circuits are actually synchronous, purely synchronous circuits. But sometimes you want some asynchronous operation. So when that time happens, then you need to consider them. Okay. Here we need to consider a few issues around timing considerations. And these are not so key, but I think we need to understand them as well. So we've already looked at setup and hold times. Setup and hold times. Hold time, setup is the time prior to the active clock transition that your inputs should have reached their so you use your inputs certain setup time for them to stabilize before you bring the active clock transition. And so setup time is that minimum time where your states need to have stabilized or to have changed into their current states before you give the active clock transition. We said that the clock transition and the inputs should not be happening at the same time. The holding time is the time after the clock transition, after the active clock transitions, for which those inputs should remain in those states so that you enhance reliability. Then we have propagation delays. Propagation delays mean that if you have a flip-flop, let's say D flip-flop and Q. If I give my clock transition here, if I give it at time T1, there is a delay up to time T2. In other words, this is D and this is Q. So there is a delay between you giving the active clock transition and this D value being input into the flip-flop, appearing at the output. There's that propagation delay, and that propagation delay can be anywhere from 10, 15, 20 nanoseconds to even 100 or 200. So those are the propagation delays. You can see you have a clock signal and your output. So when you give the clock signal, the idea is that your inputs would have gone in before. Those are your inputs, say J and K. And this is, if you remember, this would be your setup time. So when you give the clock transition, the clock is active the moment it goes through the 50% point. And then your output was still 0. You're trying to change it to 1. You're trying to set it. It is 0. So once you give the clock transition, the flip-flop starts the operation of changing that output to 1. And the output will begin to rise. And the moment it passes through its 50% point, we say it is now 1. But it will increase up to 5 volts or whatever. And this is your propagation delay. And we say it is the delay of the transition from a low to a high. That's why we have TP, low, high. You can see that the transition is moving from a low level to a high level. This side, it is propagation delay, high to low, because here, presumably, your output was initially 1, you want to make it a 0. So you give the clock transition at this point, and the transition of the output actually passes the 50% point at that point. So this delay is our propagation delay from the high level to the low level. The same, what we call the propagation delays are also specified for pre and clear, because the moment we clear like preset here, you give your preset command at this point, but let's say your command of preset is that pre, and that's the 50% point. But you are presetting, meaning that the transition is going from 1 to 0. That's your preset, and that is your output. The output will, at that point, once you give that command, it will take a bit of delay before it goes through its 50% point. So this is for exactly similar, but in terms of pre and clear. And this is still going to be TP, which is the propagation delay from a low to a high. So you can specify these propagation delays for not only the inputs and outputs, but also between the pre and clear, and also the outputs, between these asynchronous inputs and the outputs. Now, obviously, these ICs, these flip-flops will have different transition times or hold times and so on. And so when it comes to times, they will have a batch of, say, 1 million of them and test them, and they will have different times, but they will record the highest time. The one that records the highest time, that becomes the highest time for all of the flip-flops. Even if these flip-flops are by the same manufacturer, same type, same model number, and so on, they will have differences in operation. Some will respond faster than others. So they will find the maximum value of the T, say P, H to L, and T, P, low to high. These will be different, by the way. That's why we specify them differently. The values will be different, but they will always take the maximum out of a batch. It means that all of the others can also meet those time requirements, but you're confident as a buyer that if I pick any of these, it will be within this range of the propagation delay. Daphne?
Excuse me.
I can't hear you well.
Setup and hold time.
I can't hear you well. Can you repeat that?
Please explain this because I haven't understanding.
For the setup and hold time?
Yeah, from
Yes, I think I explained this last time actually, and I think it was Wednesday. Okay, I believe it was Wednesday, but we said that the setup time, in fact, let me just, because I've explained this, so you can always go back and look at it. We said that for the setup time, it is the time prior to the clock signal for which you want your states or your inputs to be in their states. So if I want a 1 and a 1, I'm going to move these into, or move them into, maybe at time t naught, let's say J and K. I want them both to be 1. Okay, so that is a 1 and that is 0. I will move them into these states and then wait a certain time so that at T2 I give the clock. Now this time delay is what we call setup time. The hold is once I've given the clock, I still need to wait a certain time before I change these inputs. So this is my TH. And so if I look at, for example, D and clock for the D flip-flop, I need to move my D, let's say D was initially, D naught was a 0, I need to make it 1. I will move my, you will transition D, which was initially 0, and you move it to the one state. It reaches the one state the moment it passes through that 50% position. Now, we are saying that you should wait a certain time before you actually change the clock. Okay, you need your inputs to be in the states you want them for a bit of time before you give the clock transition. So let's say maybe you give the clock transition at that point. That's again 50%. Now this is the this difference is what we are calling the setup time. And once again, you can change this again. Maybe this is the clock, okay? But you should keep this within that period for once you change the, once the clock transition, but we need to measure it at this point. So from here, you need to keep this in this state for a bit more time, which is your holding time. Gems, of course, they have some resistance. Everything always has resistance. Every circuit has resistors in them. I can't tell you the range because there are various ranges. There are various types. It depends on the operation. Now, we had already talked about setup and hold times. Now we are talking about propagation delays. That if I give a command, at the day before command, the effect of that command is realized at the output, at the Q output. So that is the propagation. What that because if for instance, I change this and before the output is realized, I make another change at the input, the flip-flop will be confused. So you need to know the propagation delay so that you can wait for that propagation delay before you make extra changes. So if we continue with this, there's something called maximum frequency. The flip-flop has a maximum frequency. We are going to see how we can calculate that maximum frequency, but that maximum frequency is determined by the clock. So the clock frequency can be up to a certain value. If you clock the flip-flop beyond that frequency, it may not operate as you expect. So again, you have a range of flip-flops, and you can test them, and they will have different maximum frequencies. But in this case, instead, as opposed to the time component, in this case, you're going to record the minimum value. So you get the minimum. If I test 10 flip-flops, I will record the frequency, the maximum frequency, as actually the minimum of those 10 flip-flops. Why? It means that the other ones are also capable of performing at a faster frequency, but when I'm selling my goods, I can say, okay, so maybe some of them reached 30 megahertz, others 25, others 20. I will record 20 megahertz, but if somebody picks whichever they pick from these, at least each one of them is able to support 20 megahertz frequency. Another one is the clock pulse high and low times. This really means how long the clock stays in the up position and how long it stays in the low position. So this is the one, and we record it, we denote it as TW low and TW high. It is like width, time width of the pulse. Obviously that has something to do with the frequency. And then for the piece preset and the clear, you can also have the same. You can see preset or clear, it has also, in this case, they are active low, so we only consider the low state. So how long should it be in the low state? Okay, and you're measuring through the 50% points, and that is TW in this case low. Clock transition times, so that this is we talked about this between the 90%, 10% to 90% points. This time is the transition time, okay? maybe TT, which should be for TTA less than 50 nanoseconds, for CMOS around 200 nanoseconds. Okay, so we have some actual ICs. We, for instance, have the 7474. These are model numbers. We have the 74LS112. Usually these ones, like the 74LS, the LS is usually, this is TTL, and these are CMOS. So CMOS uses the symbol usually HC or C, but it's usually HC. And TTL usually uses the symbol LS or just S, but usually LS. So if you see those, you know, you know what it means basically. You know that either this is TTL or if it is HC, it is based on CMOS technology. So you can see here some values. Okay, all these are in nanoseconds. And what we can see here is that you can see the setup time is a bit, you know, around 20 nanoseconds. But what we see here on the holding time is that it is near 0 or 0, essentially. This is the holding time. It is the time after the clock transition that you should maintain the states in, or the inputs in those current states, so that the thing can work. But you can see that that time doesn't have to be long, certainly not as long as the setup times, because setup times you want your states to actually stabilize in those states. So it takes a bit of time. But for once the clock comes in and the flip-flop has captured the inputs, you don't need to really hold longer. Secondly, we can see that the 74C, 74 is much slower than the 74HC112. So CMOS, based on the metal gate, is much slower than the high-speed CMOS, something like that. But in general, you can see the values don't have to be the same, but you can see that they are quite close to each other. Abemasko, I don't know if you mean slides or videos. Please be specific on that. Kwebiha, these are not applications. These are just what I can say. These are just specifications of these gates. So when you go and buy that dual edge trigger D flip-flop, it will come with a data sheet, and in the data sheet they will show you these values. And so these are not applications, but these are specific ICs. So a 7474 is an IC. Its TS is 20 nanoseconds. Its holding time is 5 nanoseconds. Excuse me. The propagation delay from high to low for the clock is 40 nanoseconds. From low to high is 25 nanoseconds. Now the propagation delay high to low for the clear is 40 nanoseconds, and high to and low to high for the preset is 25 nanoseconds. But actually, this should be, I believe, high to low, and this should also be high to low. I think it should also be high to low, because you know these ones are moving from the high state where they are inactive to the low state. So, and this is the width of the pulse, of the clock pulse. Okay, so 37 nanoseconds. If it's a low pulse, and if it's a high pulse, 30 nanoseconds. And these are this is the width of the pulse, which is a low pulse. Okay, I think this is fine actually. It is high to low and low to high. If it is, these will be low pulses, the active pulses will be 30 nanoseconds for a 7474. And finally, the frequency, maximum frequency in megahertz is 15 megahertz. So you can see that it can operate up to 15 megahertz. This one operates up to 30 megahertz, and so on and so forth. Yes, I promised to take you through troubleshooting, but I might do that. Okay, I'll try and start with it on Wednesday, but also you can go through it on your own actually. But I'll try to take you through that. Don't you worry. Although I believe that because we did troubleshooting for flip-flops, I think, and these are not necessarily so different. Was this at the back of chapter 4? Just remind me. And with the Abemas core, yeah, but when you should at least, yeah, the videos I upload, and Abemasco, you are always here, so I don't even know why you need the videos. But the videos I've been uploading, and they are in the link, and I told your class representatives. I also told some other students or students that the videos are in the link. They are there. If there are some videos you don't have, see if they are there. I will take them down when I'm uploading the new videos because I don't have space on my drive. Okay, so here are some questions as we end. So we assume that Q is equal to 0. How long will it take Q to go high when a PGT occurs at the clock input of a 7474? So that means that is the how long can it take Q to go high? So that means that is T, that's propagation delay from low to high for clock or after clock. So A will be the propagation delay from low to high because they are telling you how long can it take Q, the output, to go from high, to go high. That means it was low. So it is going high when a PGT occurs. So that is TP, low to high from the clock. It is what? 25 nanoseconds, I believe. Assume that Q is 1. How long can it take Q to go low in response to the clear input for a 74HC112? So that is TP high to low from clear, okay? And so if we look for the clear here, it is TP high to low, yes, clear, and we are looking for that. So I think that's 41 nanoseconds. Can you do C for me and let me know? What do you have? I see some of you are saying lecture 8 and lecture 11. Yeah, if you don't have them, it's okay. You can survive. If any student has them, you ask around, maybe they have them. If you don't have them, yeah, that's okay. Musa, I don't understand which part you've not understood. These values, we are taking them from the table. in fact, I'm going to leave this for you to read because I think you can. I think you can understand. You go and read this stuff. It is very easy. They are telling you, and I taught them actually here. This stuff. They are telling you that we have two different times. We have propagation delay And this delay is caused by when you effect changes at the input, how long does it take for those changes to be effected at the output? And then the delays are either low to high or high to low. So when you see a question like that, if we are assuming that Q is 1, then it means that Q will go low. So we are looking for the propagation delay from high to low. And then they've told you in response to a clear input. Remember, it can also be in response to the clock. Okay, but in this case, it is in response to the clear input. And for a 74LS112 flip-flop, okay, 741LS, 74LS. Okay, so let us look for that. That is, yeah, for a 112, sorry, 74HC. So we are looking for TP high to low for the clear input for that, which is 41 nanoseconds. And this is a table of values that are factual. These are not, we are not making these up. I think for the narrowest pulse that should be applied to the clear input, the narrowest pulse is TW. That is the width of the pulse of the 74LS112 flip-flop. TW, the clear should be basically low. Okay, if we were doing the clear, it is low. So TW low, you can see pre or clear, both of them are the same. And 74LS112 is 15 nanoseconds. So for those of you who have not understood, this is really easy. There are a bit of stuff to read around this. Maybe it will help you. But please go and try to understand this. Which flip-flop in table 5.2a, did the people give me these answers or they stopped working? Don't stop working. I saw a few of you. Please continue. A flip-flop in table 5.2, this table is 5.2 in the book, requires that the control inputs remain stable after the occurrence of the active clock transition. So this is after. So that means TH, the holding time. If it was before, that would be setup time. So you really need to take these things seriously, because clearly some of you are confused, and I don't see why, because these are quite easy. So they are asking which flip-flop requires that the control inputs remain stable after the occurrence of the active clock transition. It really means that is Rosemary Nankabirwa. Is this a minister? Oh, there's a minister called Rosemary. I don't know why you are. Next time I'll take you out. So this is really, if you look at the TH, this is 000, meaning there is no requirement. So the one that requires a holding time is the 7474, as simple as that. And then for which flip-flops must the control inputs be held stable for a minimum time prior to the active clock transition? This is TS, okay? This is the holding stable for a minimum time before. Prior is before. That is TS. So they are saying which flip-flops must the control inputs be held stable for a minimum time prior to the active clock transition. So all have a holding, all have a setup time, as you can see. Yeah. Okay, so let us stop here. It is midday. It's actually a bit past midday. Did you do the quiz on you did the quiz, right? On Friday?
Yes.
Okay. I'm going to give you some group work to do this week. And also please note that we are going to have another test within the next 2 weeks. And that test will cover flip-flops and combinational circuits. So around December, mid-December, we are going to do, it could even be next week on Wednesday. So please kick on and try to read. I try to make this course busy because when I don't make it busy, people fail. Can you imagine? So I'm trying to help you. Meaning a flip-flop with a higher hold time possesses the better stability. No, not Kasiswa Kamoga Alan. It doesn't mean that. It means even these ones which don't have a holding time are stable. It's just that they don't need to hold. In fact, in a way, you could say they are better. since they don't actually need to hold on, but it doesn't mean that they are more stable. The stability, all of these flip-flops require stability. Some get it after holding, others get it even without holding. So what would you say is better? Maybe the flip-flops that don't require hold time are better because I think they can be faster. Yes, so I'll be sharing some group work with your class representatives. Please keep an eye out for that. And once again, do them as groups. And if anyone doesn't contribute, write to me a private email. You can even text me and let me know. Have a nice day, and we will meet again on Wednesday. Take care. Bye.